Hello students. Dear students, I request all of you please subscribe my channel Venus Academy if you are not yet subscribed, and don't forget to click on like button and bell button. Dear students, we are going to learn chemical reactions of carboxylic acids. Let us see the chemical reactions of carboxylic acids. Yes, so carboxylic acids are very acidic compounds which form salts with metals and bases. Benzoic acid, let me take benzoic acid. When I treat it with sodium metal, it is going to form sodium benzoate. So this is salt, sodium salt of benzoic acid, sodium benzoate. Okay, so this is salt can be formed using sodium metal, and it can form, let me take it as any acid, not only this carboxylic acid, any acid, and it can form salt with NaOH to form this ONa plus water. If I use sodium bicarbonate, it is very important. Carboxylic acids form salt with weak bases also. When it comes to phenols, phenols react with only sodium hydroxide, strong base, and form salt. Whereas phenols will not form salt with sodium carbonate or sodium bicarbonate. Right? It is the distinguishing test for the acids and phenols. Sodium bicarbonate, which is a weak base, and say it is water, aqueous solution, or whatever it is. Right? I can form or isolate this sodium salt of acid, plus it is carbon dioxide, and what is left over? Water. This is going to be the reaction. Yes, students, let us take some. Yes, students, let us take one by one chemical reactions. The first one is esterification. I am going to stress on important things. So esterification, let us take carboxylic acid plus alcohol. Let me take ethanol, CH3, CH2, OH. And if I do the esterification in presence of acid, H plus ions, I am going to get R, O, and this is the alcohol part is going to be attached. This is the key point. So oxygen is coming from alcohol. Oxygen is coming from alcohol. During cleavage, this oxygen is going with alcohol, and this oxygen is coming from alcohol part. This is ester. The name is ester. If I write the mechanism, so when I write H plus ions, carboxylic acid, yes, it will have lone pair electrons. Dear students, it also will have lone pair electrons. So the oxygen, which is sp2 hybridized, is going to share its lone pair electron more easily than the oxygen having sp3 hybridization. So it easily donates lone pair electrons to form R, O, H is here, positive charge, and OH. Yes, now it is going to take up, we are doing, let us say in water, sorry. So now it is going to take up alcohol. Let me write R, OH here, and this OH is going to attack onto the carbon on the oxonium carbon, oxonium ion to give R, CO, H, and already this OH is here. I am writing down this OH. Now O, R and hydrogen is here. Yes, so what is the hybridization here? It is sp3 hybridized carbon now, tetrahedral. This is sp2 carbon. This sp3, it exchanges, proton exchange takes place, proton exchange, where it is having this proton will be exchanged by this oxygen to give an intermediate where R, O, positive charge, and O, R. Now it is very easy, it loses H plus and to give R, O, double bond O and O, R. Yes students, so minus water. This is nothing but ester. So the mechanism, key thing is that the oxygen which is coming here is from alcohol part. So I can write alcohol part. So if it is labeled with oxygen isotope, then it will be here. So this is what you have to remember. So this oxygen is coming from alcohol part. Okay, Yadav. So acid upon reaction with alcohol gives esters, and the oxygen part is coming from alcohol part. Right, students? So the hybridization, when you see the hybridization of this carboxylic acid sp2, so it easily forms sp3 hybridization to get out of strain. So it easily takes up proton to form this oxonium ion. Oxonium ion takes up this alcohol oxygen to give this intermediate where it proton exchanges. Yes, or I can write in different form. So it loses this, it gives intermediate, no doubt, it gives intermediate ether, and it takes up proton, any one of these two, and it is going to form this same intermediate. Right? Same intermediate. Now it is going to lose water to give ester. Right, students? Let us take some examples under this. So I can take, if I take benzoic acid, you will be tested on this part mainly. And alcohol, ethanol, I can write like this, ethanol and acid. And moreover, this reaction is reversible reaction. As soon as the ester is formed, you have to remove off this ester, or you have to take care that water should not present. Otherwise, it is going to hydrolyze back. Yes, there are techniques to use Beanstalk apparatus and like that, and it is synthetic techniques. Don't worry. So at this stage, use H plus ions and see that ester and there should be no water. So you should not write water here. If it is water, it is backward reaction. So this is going to form ethyl benzoate. Like this, you are going to get esters. Right, students? Next. Then reaction with phosphorus pentachloride or phosphorus trichloride or thionyl chloride. So during alcohol's part, we have come across this type of reaction where OH group is going to be substituted with halogen. In alcohols, we have seen that halogen. Yes, students. In alcohol part. Similarly, when I take this carboxylic acid, I am going to get acyl halide. Carboxylic acid. In presence of these reagents, any one of these reagents, I am going to get acyl halide. So among these, if I use PCl5, for example, carboxylic acid, if I use PCl5, phosphorus pentachloride, I am going to get RCOCl plus POCl3 plus HCl. Yes, students. Or if I use same acid plus PCl3 or PBr3, I can use PBr3 also. However, that PBr3 if I use, there is another reaction it is going to undergo. So PCl3, let us stick on to this PCl3, RCOCl plus this phosphorus, PO H3 PO3 plus it is going to form H3PO3. However, the removal of POCl3 it is very lacrimatory, means your eyes will what I can say. So tears will come, right? So it is lacrimatory. Use of this PCl5 and PCl3 will be lacrimatory. So it is very tough to handle this type of reactions in laboratory. So the easiest method or the best method to make acyl halides is use of thionyl chloride. Thionyl chloride is a liquid, and when I treat this thionyl chloride with acid pot with thionyl chloride, I am going to get acid chloride RCOCl plus sulfur dioxide, which is volatile and it is not going to stay in the reaction mixture, and HCl, which is also going to be out as gas. HCl gas. Right, students? So carboxylic acid in presence of thionyl chloride, you are going to get acid chloride, and the other sulfur part is going to be as sulfur dioxide and it is going to be HCl. These two are volatile, and simply I can get this acid chloride and use it for other reactions. So this is how reaction with phosphorus halogens is going to form acid halides. Next, students, next reaction with ammonia. With ammonia. So ammonia is a base and it is an acid. What is going to form? It is going to form first salt, then it is going to form amide. For example, if I take acid plus ammonia, it is going to form RCOONH4 plus and minus, and this when I heat it, it is going to lose water and to give amide NH2. So this is amide, students. Write down amide. For example, if I take acetic acid and treat it with ammonia, I am going to get this salt ammonium acetate. It is a buffer. Ammonium acetate, it is a solid part. Ammonium acetate is a buffer solid where it is a salt of weak acid and weak base. So it is going to be act as buffer. Ammonium acetate, when I heat it, it is going to lose water to form acetamide. This is acetamide. Similarly, if I take benzoic acid and treat it with ammonia, I am going to get ammonium benzoate, and this ammonium benzoate upon heating it loses water to give benjamide. And important thing, Gabriel amino acid synthesis, we will learn this. Phthalic acid, where we prepared from tetralone, this phthalic acid upon reaction with 2 moles of ammonia, it is going to get salt of this phthalic acid, and this upon heating it is going to form amide, diamide. So this, from this phthalic amide, phthalamide, this is phthalamide, spelling is important students. Phthalamide. This phthalamide upon vigorous heating in presence of base, it is going to lose 1 mole of this hydrogen ammonia. At high temperature it is going to lose minus ammonia to get phthalimide. This phthalimide plays a very important role in Gabriel amino acid synthesis. So during that synthesis or the name reaction I am going to explain this importance. So this is phthalimide. Write down the spelling. Phthalimide. Yes students. So phthalimide you are going to take. Next, reduction of carboxylic acids. So what is reduction? Again, if I write Leo-Zer, so it says lending of electrons oxidation, gaining of electrons reduction. With our context, it is addition of hydrogen is reduction. Addition of oxygen is oxidation, addition of hydrogen is reduction. Let us take carboxylic acid. This is carboxylic acid. When I do the reduction with lithium aluminum hydride, it is going to reduce or it is going to add 2 hydrogens to give alcohol. Yes, so this lithium aluminum hydride, when it comes to chemoselectivity, means this lithium aluminum hydride is going to reduce all types of compounds like carbonyl compounds, nitro to amine, esters. So LAH is not selective. It is not selective reducing agent. It will reduce ketone, aldehydes, nitro, esters, and all these groups are going to be reduced to alcohols or amines. Yes, so in your starting material, if you are doing some synthetic part, in your starting material, imagine that there is an nitro compound, for example CH2, nitro and COOH, and you are in need of this compound, and halogen also. Halogen also reduces this LAH. And nitro, you are in need of this compound. What is the reagent? Optional reagent. Yes? So there is one reagent where nitro, ester or halogen. So nitro, ester or halogen are going to be no effect or intact. The reagent is diborane, B2H6. Dear students, please remember, diborane is very important reagent which is chemoselective. Means it chemoselectively reduces only acid to alcohol. Acid to alcohol. Yes? So acid to alcohol, it is asked in NEET students. So diborane was asked during 2018 NEET. So diborane can be used for the reduction of acid to alcohol. It is chemoselective. So diborane is nothing but the structure BH3 and BH3. You will get BH3 like this. Yes, diborane. It is dimer of borane. So this diborane, however, it is costly and very tough to handle in synthetic chemistry. But if you are in need of this specific compounds, this reduction of only acid is required, you have to use diborane. Yes, if I use lithium aluminum hydride, what is going to happen? Any guess? So this compound is going to be amino alcohol. Right? But I am in need of this nitro. So here diborane comes. And one more, the common reagent what we learned is sodium borohydride. Sodium borohydride is not going to work or not going to reduce these carboxylic acids to alcohols. Yes, students. So this is how reduction of carboxylic acids chemoselectively done by diborane. Whereas lithium aluminum hydride reduces carboxylic acids to alcohols, but the selectivity is very low with respect to other functional groups also are going to be reduced to different compounds, suppose carbonyl compounds alcohols, nitro to amine, ester to alcohols. So diborane is key point, please remember this students. Next is decarboxylation. Decarboxylation of carboxylic acids. So when I treat acid with base or soda lime. Soda lime is a mixture of NaOH plus calcium oxide in 3:1 is known as soda lime. You make it as soda lime. Right? So this soda lime is going to form first, say this is ONA, and this sodium salt when I heat it, it is going to lose carbon dioxide. So this carbon dioxide is going out and you are going to get alkane. So decarboxylation takes place. Dear students, most of the times even simple heating also decarboxylation takes place. For example, benzoic acid, thermal decarboxylation is known, students. So it loses carbon dioxide, right? So you may get only heating also, you have to write benzene, carboxylic acid loses carboxylic acid. So decarboxylation is known. Another decarboxylation method what we learned in previous class is Kolb's electrolysis. So in this it is a free radical reaction where if I take 2 moles of, for example, CH3 acetic acid and do electrolysis, I am going to get ethane, CH3 plus carbon dioxide plus hydrogen. This is sodium salt if I take. Yes, students, let us see the mechanism of this. So the mechanism is very simple, students. So when I take this methyl O, it is minus and plus, O minus, and it takes up electrons, 2 electrons, it is 2 moles, CH3 minus 2 electrons. The 2 electrons if I remove from here, or let me write 1 electron minus, it is going to form CH3 CO free radical. This free radical further in next step it is going to form methyl radical plus carbon dioxide. This methyl radical, it is methyl free radical plus another methyl free radical is going to form ethane. Yes, students. Next, so at cathode, what is going to happen? Water is going to be there plus, and the electron which is coming here will take up this and form OH minus and H free radical, and two H free radicals is going to form hydrogen. This is how it is going to undergo decarboxylation. The usual method is soda lime. Soda lime method is very common, students. So carboxylic salts, under using soda lime, it is going to lose carbon dioxide. Next, substitution reactions on alpha carbon of carboxylic acid. Right? So what is alpha carbon? R CH, and this is alpha carbon. And this alpha carbon hydrogen will be substituted in presence of halogen. Let us write chlorine or bromine in red phosphorus. Using red phosphorus, it is going to give alpha halo carboxylic acid. So X can be chlorine or bromine. And this alpha halo carboxylic acids are very, very important synthetic starting materials for the preparation of amino acids. Right? So this reaction is known as Volhard-Zelensky reaction. Dear students, I have made already name reactions. Under name reactions, HVZ reaction, there I have explained in detail mechanism and number of examples. Anyhow, at this stage, the mechanism follows like this. The red phosphorus, what is there? Phosphorus will react with bromine from PbR3. Yes? PbR3. This PbR3 is going to act real reagent for the halogenation of alpha carbon. So the acid group, what I am going to take, this PbR3, it is observed that even if I use PbR3, it is going to form alpha halogen. In previous example, PCl3 examples we have seen. So it is going to form, first it is going to form this acyl bromide. Why this mechanism is taken? Because acyl bromides, even without using phosphorus, are going to give alpha halo bromo compounds, alpha halo carboxylic acids. This acyl bromide, so these acyl bromides can enolize to form R C hydrogen double bond CO and bromide enolized carbon. This enolized one, it will take up bromine. Since we are adding bromine, so it takes up bromine to give R C hydrogen. No new bromine has come here. O double bond O bromine. So this dihalo compound is going to react with another mole of this carboxylic acid to exchange this bromine with this water to give OH group to give R H bromine and CO OH, and again this acyl bromide, and it will be recycled in the reaction mixture. So acyl bromide will be formed, and the product is alpha halo carboxylic acid, which is the product of HVZ product. So Volhard-Zelensky reaction gives alpha halo carboxylic acids. Next students, so if the carboxylic acid is aromatic compound, then what is the fate? So let us take benzoic acid. Benzoic acid, what is the nature of this benzoic acid? Is it electron withdrawing or donating? it is electron withdrawing group. It withdraws electron density or these electrons from benzene ring. So it is electron withdrawing group. This electron withdrawing group is deactivating group. Electron withdrawing groups are deactivating groups. Deactivating groups on aromatic ring, they orient the incoming electrophile to meta position. These are meta directing group. Carboxylic acids are meta directing groups. Since it is a carboxylic acid, it is very, very important, students. Friedel-Crafts alkylation or acylation is not going to take place. Friedel-Crafts reaction are not done on carboxylic acids. Why? It easily loses H plus ions. We are going to use dry aluminium chloride. This dry aluminium chloride is going to form complex with carboxylic acids because it gives H plus ions. So further it will not move forward because it forms salt with carboxylic acid. So that is why Friedel-Crafts alkylation is not going to be done, right? So, and one more, already I have explained, nitro compounds also you are not going to use in Friedel-Crafts reaction. It is also not going to undergo Friedel-Crafts reaction. That I have explained under Friedel-Crafts acylation and alkylation reaction, students. So why it is withdrawing group, that is why it is not going to undergo Friedel-Crafts reaction. So it can be used as solvent. Nitrobenzene is used as solvent in Friedel-Crafts alkylation reaction. Anyhow, so benzoic acid part, let us take some reactions. Nitration. So nitration reaction of aromatic ring is aromatic electrophilic substitution reaction. Yes, students. So aromatic electrophilic substitution reaction. So benzoic acid upon reacting with HNO3 and sulfuric acid, I am going to get meta-nitrobenzoic acid. So if you are asked to make meta-nitrobenzoic acid, don't write this acylation reaction or carboxylation, nitro to this. So do the nitration. What are the steps involved as usual? So HNO3 and H2SO4. Plus HNO3 is going to form HSO4 minus plus OH. It is going to give H plus ions. Here it is going to form positive O, and this is O minus, and it loses NO2 plus. This is electrophile. Generation of electrophile takes place, and this electrophile will take up this, will substitute this meta hydrogen, and at the final stage it loses hydrogen to this sulfate ion to give sulfuric acid back, and it is going to be substituted with nitro. Yes, similarly halogen also, bromine in presence of ferric bromide, it forms, for example, bromine electrophile, stress. Ferric bromide, it is a Lewis acid, it is going to form bromine plus ferric bromine taken 4 times minus, iron minus. So this electrophile, if I take same benzoic acid and do the bromination, bromine in presence of ferric bromide, I am going to get metabromo benzoic acid or 3-bromo benzoic acid we are going to get. So this is how we can do electrophilic aromatic substitution on carboxylic acids, aryl carboxylic acid. Yes students, so let us take some uses of carboxylic acids. What are the uses? So some of the carboxylic acids, if I take formic acid, it is used in textile industry, right? Rubber industry or polymer industry. And the important thing is acetic acid. This is vinegar. What is vinegar? Food additive. Yes, food additive. And important thing is, if I use this sodium benzoate, what I prepare using salt formation is food preservative. So you will find this sodium benzoate in some food particles as a solid part, or you will get in a bag of this sodium benzoate too, which prevents from oxidation. And especially this hexanoic acid, at the beginning I have explained this hexanoic acid, adipic acid, hexane dicarboxylic acid, adipic acid is useful for the preparation of nylon 66. It is a polymer. Nylon 66 is a polymer. It is useful. And esters, yes, can be used as perfumes. Esters as perfumes. And moreover, the large number of carboxylic acids you come across are fatty acids. These fatty acids, glycerol esters, fatty acids, glycerol esters are soaps and detergents. Yes friends, these are some common uses of carboxylic acids. Dear students, I hope you enjoyed this lecture. Thank you students, thank you for watching this video. Please subscribe my channel Venus Academy if you are not yet subscribed, and don't forget to click on like button and bell button. Bye. We will meet again with new topic. Till then, bye. Arigato gozaimasu. Thank you. All the best. Thank you students.